And we are moving to the final speaker of today's session, and that's Sarah Gonzalez Henao, who is a PhD student at the Institute of Astrobiology in Colombia. And she will present a talk to us about the conversion of polycyclic aromatic hydrocarbons to a biologically extant quinone.
Hi everyone, can you hear me?
Hello, hello. And I don't hear you, but it might be again the issue with my settings. Okay, Albert confirms that he can hear, so I'll just restart my browser. And Sarah, please share your screen and take it away.
Can you see my screen? Hello?
Yes, it's working.
Okay.
We hear your slides. Looks very nice.
Okay, thank you. Hello everyone, my name is Sarah Gonzalez Henao. I'm from Colombia, and today I'm going to present a recent published study which is called Planetary Minerals Catalyzed Conversion of a Polycyclic Aromatic Hydrocarbon, PAH, to a Prebiotic quinone. To start, polycyclic aromatic hydrocarbons, PAHs, are organic molecules composed of multiple aromatic rings and are one of the largest classes of compounds of the solar system and the observable universe. These compounds are ubiquitous in extraterrestrial environments where they arise from polymerization reactions of smaller organic precursors. Moreover, they are ubiquitous on modern Earth, where they are produced from the incomplete combustion of carbonaceous materials and are considered a priori environmental toxins due to their carcinogenic potential. Moreover, PAHs were also abundant on the primordial Earth, where they could have functioned as molecule precursors for seeding origins of life chemistries. And in addition, these molecules have been detected in carbonaceous meteorites, comets, interplanetary dust, planetary atmospheres, and interstellar media. Within these environments, PAHs can interact with mineral phases, such as phyllosilicate clays and metal oxides, to produce oxy-PAHs, such as redox active quinones, like 910 anthraquinone, which is a focus of study here. And phyllosilicate clays are common in terrestrial environments, and clay minerals are of particular interest due to their capacity to exchange reactive cations with molecules within their interlayer regions. And these properties, combined with high surface areas, continue to motivate experimental efforts to characterize the extent to which mineral phases might act as reactants and/or catalysts in prebiotic systems. Two clays studied here are kaolinite, which is a clay mineral with simple structure. This is described as a one-to-one clay mineral, where each layer consists of a tetrahedral sheet composed of silicon and oxygen ions bonded to an octahedral sheet composed of oxygen, aluminum, and hydroxyl ions. On the other hand, we have montmorillonite, MONT, which is a very soft phyllosilicate. It's a 2-to-1 clay, meaning that it has two tetrahedral sheets, sandwiching tetrahedral sheets of silica, sandwiching a central or octahedral sheet of aluminum. Moreover, phyllosilicate minerals are planetary relevant and are also distributed over the Martian surface, where metal oxide minerals have been proposed to be involved in facilitating abiotic reactions important for bioemergence. And for the purpose of this study, we use the Mohave Mars Simulant, as you can see here, which is composed of basaltic minerals from the Mohave region. And in this table, you can see the composition of the MMS and the composition of Mars, which is closer. We use here the MMS2, which is closer to the chemical composition of Mars than any other Martian simulant. Other planetary relevant molecules are quinones, which are oxy-PAH derivatives in which one or more of the hydrogen atoms of the aromatic ring is replaced by oxygen to form redox-efficient carbonyl groups. Quinones, like ubiquinone and the plastoquinone that you can see here, function in various redox states in electron transport change, essentials for life, for example, in photosynthesis. And moreover, PAHs have been hypothesized as precursors for the prebiotic synthesis of quinones and have been proposed as plausible stabilizing agents and photochemical pigments in primitive membrane systems. Aromatic alcohols and quinones, like the 910 anthraquinone that I mentioned earlier, which is the focus of study here, have been prepared from small PAHs, including naphthalene and anthracene, in simulated astrophysical environments. Here in the study, we use anthracene because it's simple, it's manageable, and it's a solid PAH consisting of 3 benzene rings derived from coal tar, and is the simplest tricyclic aromatic hydrocarbon. And discussion of the importance of anthraquinone for origins of life is perhaps a bit paradoxically, as the compound exhibits appreciable toxicity at relatively low concentrations. However, this compound displays a prominent role in biology, as I mentioned earlier. And it's important to note that apart from our previous study of the thermal kinetics of conversion of anthracene to anthraquinone and MONT, this was our foundational study, we are aware of no studies addressing the thermal quinone production from our representative commonly detected PAH on multiple mineral substrates in the context of origins of life. Therefore, to fill this knowledge gap, we assess the potential of the clay minerals MONT and kaolinite and the Enhanced Mohave Mara Simulant (MMS) to facilitate the conversion of anthracene to anthraquinone. And upon establishing that the catalytic potential of the minerals, we quantify the kinetics of conversion to anthraquinone and the loss of anthracene and anthraquinone over different temperature regions relevant to astrobiological studies. Therefore, briefly, we prepared reaction tubes with a Bunsen torch. We added 20 milligrams of substrate plus anthracene. We incubated the reaction mixture at temperature. We assessed the color change of the reaction. Then we extracted the reacted contents of the tube with organics, in this case DCM and toluene. We centrifuged, and then we analyzed the extracts in the gas chromatography mass spectrometry. And as I said before, in our previous study, the catalyzed thermal conversion of anthracene to anthraquinone was assessed using larger volume ceramic crucibles, like you can see in this picture, which yielded very low anthraquinone production over 25 to 250 C. Therefore, to improve this, in this study, we fabricated small diameter glass reaction tubes, which yielded higher anthraquinone production, as you can see here in the graph. And this difference is presumably due to the excess of anthracene and anthraquinone vapor losses from the more open crucibles relative to the far more volumetrically confined reaction in the tubes. In this study, we explored the capacity of 3 mineral phases to facilitate conversion of a PAH to anthraquinone over a wide range of temperatures, and the substrates included are MONT, kaolinite, and MMS. And after establishing that the desired reaction still occurred in the reaction tubes, it was necessary to determine the influence of temperature on anthraquinone conversion. And we showed that all mineral substrates catalyze anthraquinone conversion up to 500 C. And in the graphs, we can see that apparent rates of anthraquinone formation displayed sigmoidal relationships for MONT and KAO, which suggest saturation of catalytic sites, or perhaps loss of anthraquinone or anthracene at higher temperatures. While for the Martian soil simulant, we show that it displayed a quadratic relationship suggesting that catalytic sites are not there saturated, perhaps due to the greater loss of anthracene or anthraquinone. Moreover, maximum rates of anthraquinone formation were compatible on the MONT and the Martian soil, as you can see here, while those measured for KAO substrate were lower than on the MONT and the Martian soil. And it's important to note that conversion efficiency to anthraquinone in our previous study was 0.06% using the larger crucibles and lower temperatures. However, in this study, mean anthraquinone conversion efficiencies under these new conditions were 1.9% for MONT, 0.66% for KAO, and 0.42% for MMS. And we hypothesized that losses of anthracene and anthraquinone, especially at the higher temperatures assessed, 500 C, accounted for much of the production rate curve trends observed here. And to test this, we assess anthraquinone production and loss at the median temperature of 200 C over 60 minutes. And under these conditions, maximum anthraquinone production rates were observed in the order of MONT, KAO, and the MMS. And we can see that loss of anthraquinone was observed as early as 5 minutes on the Martian soil simulant and as late as 17 minutes on the kaolinite. Moreover, after 60 minutes of incubation, anthraquinone loss reached the limit of quantitation for the Martian soil simulant, while for the MONT and the kaolinite retained anthraquinone quantitation. Therefore, to gain insight into the anthraquinone formation trends and the processes by which loss may be occurring, we characterized the kinetics of anthracene and anthraquinone loss from substrates up to 500 C. And apparent rates of anthracene loss with temperature occur in the order of Martian soil simulant, then for MONT, and then for KAO, with loss rates becoming statistically different above 200 T. This explains the exponential trend of the Martian soil due to the loss of anthracene. In contrast, for the rates of anthraquinone loss were substantially higher with temperature than those of anthracene and occurred in the order of montmorillonite, kaolinite, and then for the Martian soil simulant, with loss rates converging to the same mean values for KAO and the Martian soil. Loss rates of anthraquinone for the montmorillonite were 25-fold higher at the highest temperature assessed, which explains the sigmoidal trend and the flatten of the curve at approximately 300 T. Collectively, these findings show that loss of anthracene occurs to a much lesser extent than loss of anthraquinone, and maximum loss rates for both compounds differ with nature of the substrate. And just to conclude, we have shown that three planetary mineral substrates catalyze the conversion of a PAH to anthraquinone over a wide range of temperatures relevant to the origins of life. Use of a smaller volume glass reaction tubes increase anthraquinone conversion efficiency on MONT 100-fold. Rate curves of anthraquinone production were sigmoidal for MONT and KAO, but quadratic for the Martian soil. Loss of anthracene and anthraquinone differed with substrate, but all loss rate curves were exponential. And these loss trends suggest a viable mechanism for wider distribution of these compounds in prebiotic environments. And finally, these findings support a plausible scenario in which PAH-mineral interactions produce quinone precursors that could drive bioemergence in prebiotic environments. And that's all. Thank you so much for your time.
Thank you so much, Sarah, for your very nice talk and presentation. One of the things that I was wondering about, and which actually makes quinones very interesting, is their possible photocatalytic activity. So I haven't ever looked so much into this field, but have you seen anyone trying to use it, for example, in photoredox catalysis in prebiotic chemistry in particular?
We actually currently are now trying to see if the UV light produces the anthraquinone. Actually, my PI, Dr. Gaylor, is conducting studies at his lab now to test if UVC light can drive this conversion of anthracene to anthraquinone. And we actually are observing this catalytic capacity of the minerals to produce these quinones. So,
Yeah, so that sounds like a very interesting alternative pathway. But on the other hand, I think that anthraquinone itself could also act as a catalyst, so accept electrons and possibly promote some other reactions. So I was also curious about it, but I don't know, have you seen anyone looking at this? I mean, at this role of anthraquinone?
no, there are not many studies in anthraquinone as a catalyst because we know that in prebiotic environments, these phyllosilicate materials were dispersed into were dispersed in the earth and probably other environments, and they actually can act as the catalyst, protecting also these anthracene, these PAHs from the from the UV light to produce these anthraquinone. But there's not a lot of research in the role of anthraquinone as a catalyst.
Thank you so much. We have a question from Albert Fahrenbach. So Albert is writing, thanks for the great talk, Sarah. You show that mineral substrates can affect organic reactivity, but can different PAHs affect mineralization?
That's an interesting question. I actually don't know the answers, certainly. But I guess that PAHs are distributed over many environments. So maybe possibly they can be involved in mineralization in different planets like Mars or the early Earth. Well, they could drive these the formation of these minerals, perhaps. But it's an interesting question.
And actually, when you mentioned Mars, I saw that you also used a mineral which would be typical for Martian environments. Do you know, are there any results of any of the Mars missions which which already possibly showed the presence of PAHs there, or?
Actually, let me show you here. Why? Oh, sorry, my computer got frozen. But actually, we
yes.
showed here that there are when the reaction occurs, there are colorimetric changes in the anthraquinone production, and this could be a possible a signature or evidence for the presence of anthraquinone on Mars. Like you can see, you can use these color changes are like a signature or for the detection of this anthraquinone on Mars. Therefore, that will be an interesting approach in next missions to Mars to detect the presence of these important quinone for the emergence of life in other planets.
Yeah, so even possibly the presence of PAHs would tell us something.
Yeah, that's right.
Fantastic. Thank you so much for this really nice presentation. So it's really nice to see you here. Sarah, stay with us for the next session, which will be in more or less 30 minutes. So that's the origins of life and evolution, which will be chaired by Łukasz Kaczmarek. So we'll have some more of similar talks, but more going actually into higher levels of biological stories, more connected to biology. It was wonderful to see you here, to hear the fantastic talks today. The technology was on our side. So thanks a lot, and stay tuned for the next talks today.
Thank you so much.